PI on the project. Both of these folks are with the University of Wyoming and the Department of Ecosystem Science and Management. The title of the talk, or the work that Melanie did on behalf of the LCC last year, is Wetland Hydroperiod and Climate Change. And I think, Melanie, it's all yours. You have the control.
All right. So thank you very much for that nice introduction. And so I do have Jeffrey Evans from the Nature Conservancy sitting here in my office, as well as Charlotta Gabrielson, who is a PhD student here at University of Wyoming. And Charlotta is going to give a real brief introduction to her PhD work that kind of sits on top of some of this work, so you get an idea of broader context. And Jeff is here as well, so that all three of us can answer questions during the Q&A period. Okay, so wetland ephemerality. So I'm going to be talking about ephemerality through the entire talk, so want to start off with what we mean by this. So ephemerality is the persistence of a wetland across the growing season. So we may have highly ephemeral wetlands that dry before the season is over, so before the end of summer, have ephemeral wetlands that may dry some years, and permanent wetlands, so those that are there the vast majority of the time from year to year. So we'll keep coming back to these terms. Ephemeral wetlands are highly dynamic, and so they are the amount of water that is in them, the type of vegetation, the amount from year to year. It is very dynamic across the season and across years. But these highly ephemeral wetlands are important for ecosystem functions. And those ecosystem functions include water filtration, production of water, related plant production, so overall productivity of systems related to that, wildlife and livestock production, and important for crop production, both in the sense that they're places where water gathers in systems, and we may actually see them plow through in some years, but also in how they contribute to moisture. So they're a critically important part of the system, and also important for wildlife species such as waterfowl and their production, particularly in this area of the world, and potentially other species of concern, and just overall general biodiversity production as well. So just a reminder where we are, Plains and Prairie Potholes region, and our focus, I apologize to the person, at least one person here joined from Canada, is on the U.S. side, looking at the Plains and Prairie Pothole region confined to the U.S. portion of this LCC. And across this LCC, we have a temperature gradient as well as a precipitation gradient. So more precipitation as you move east, higher temperatures as you move south, at least in general. Within the Plains and Prairie Pothole region, this area is highly productive, but it's also very sensitive to this stochasticity from year to year. And there are multiple stressors within the PPP LCC. A couple of those include land conversion, as well as climate. So, and these climatic factors from year to year, as well as what might happen in the future. So even if we constrain ourselves to thinking about current climate and how stochastic it is, we may have flood years and drought years that have major implications both for the ecology of the system and the people in that system, where on the left-hand side of this screen, you have a road that's been flooded out in a high water year, photos from 2013, and you have drought conditions where this looks like nice green vegetation, but this is actually stunted corn late in the year that is not doing so well from 2012. We know that there is a relationship between climate stochasticity and how ephemeral a given wetland is in a given year, but we also know that there are going to be even more impacts moving forward. So we have uncertainty in our climate projections moving forward, but there are some things that we do know. If we were going to go from current conditions to projected, that across different projections we're likely to see less precipitation, but more importantly, potentially for wetlands, is a shift in timing of when that precipitation comes, and an increased temperature, and that increase being earlier in the year, which would shift this precipitation from snow to rain, both due to the shift in where that peak precipitation is coming and when that temperature shift is to convert rain into, or snow into rain. So if we look at GCM predictions for what is likely to happen across the plains into the future, we have a huge range of potential futures that include a loss of precipitation to an increase in precipitation and no change in temperature to a 15% increase in temperature, depending on what GCM or suite of GCMs you're looking at. But these are sort of the bounds of our future potential climates in this region. And that has implications for plant production, including crop production, as well as for biodiversity and impacts to overall biodiversity production within the area. So we have data that exist for wetlands and where wetlands are across the U.S., and these are a very useful data source, but we do have some limitations where these extremely small wetlands that could be important for biodiversity may be missed, and that we're looking at water bodies and this unit over time, and where for some questions we may be interested in ephemerality or gradient of what is the chance that this particular location is going to be a wetland. So we wanted to fill in that gap, and the phase 1 part of our project that I'm going to be talking about today was our goals were to quantify wetland ephemerality, so how ephemeral are wetlands, link that ephemerality to climatic stochasticity. So as we have changes in climate, how are wetlands likely to respond, and then predict that ephemerality under future climate conditions. So I'm going to step through each one of these objectives. What we did is we took this whole region, and we know we have this gradient in temperature and in precipitation, and we have 3 ecoregions that are represented. So we stratified this whole region by ecoregion and by drought risk, put down a 5-kilometer grid across the region, and then did a stratified random sample within there. We had 14 strata that actually, the conditions actually exist on the ground, and then had sample areas within those regions where we sampled at least 20 wetlands within that 5-kilometer block. From those wetlands, we collected a whole suite of field data. The most important piece for the purposes of these predictions is the location, just being able to relate the specific location of where there was a wetland in a given year. We went to just under 400 wetlands in those in about 18 sampling areas across 2 years. In 2012, remember, it was very dry conditions. 43 of those wetlands were dry. We only had 1 dry wetland in 2013. So in addition to location, we also looked at size of the wetland, its type, the soils that were presented, and some really kind of core scale vegetation data, what functional plant groups were represented, etc. Things that we could compare across that whole wide region. For those wetlands, we also collected some water quality information, including turbidity, conductivity, salinity, and alkalinity, as well as nitrate and nitrite of those different wetlands. And then also got a measure of overall depth and dissolved oxygen. At each of those sites, we also looked at the anthropogenic influence. So were there roads in the immediate area? We have a tiger salamander coming back to our pond from a road. If there was agricultural use, crop production or livestock use around a given wetland. And then we'd have this, want to take this information and use it to quantify wetland ephemerality, so link it to spatial data. And we have our wetlands at the top row there. We have all of our examples of wetlands in the field, linking those to those locations to spatial data, and then wanting to come up with a prediction of probability of each given pixel being a wetland. So we have our field data linked to remotely sensed data, and then making a prediction, a continuous prediction of probability of a wetland as a metric of ephemerality. So we have ephemerality of wetlands across years, but we also have a spatially distributed wetland ephemerality, where within a given wetland, the edges may be highly ephemeral, where some of the, as you get closer to the core of that wetland, it may become less ephemeral, and have some portion of the wetland that is less ephemeral or potentially even permanent. This example on your screen is a ephemeral to highly ephemeral wetland, but they have this gradient of the areas that dry even within that highly ephemeral wetland. So we have our 18 sampling areas. We identified 4 of those where we wanted to use RapidEye as a way to subsample those, where we have RapidEye images, 5-meter resolution data for those targeted sites, and have a 500 square kilometer block for each one of these 4 locations. And then want to use that to scale up to Landsat 30-meter data. So use our RapidEye data at 5 meter to get probability of wetlands from that, look at a wetland extent over time, what is really the bound of this wetland, use that to then relate to a subsampling that we can predict to a coarser scale and larger area, Landsat information, and then come up with an overall measure of a wetland ephemerality. And I'm going to step through this diagram. So we have our wetland classification from our RapidEye data. We want to classify that RapidEye 5-meter imagery. We had 3 time points that represented wet, dry, and moderate conditions from 3 separate years, and use random forest to come up with a continuous classification where our result is probability of being a wetland. Okay, so we have a 0 to 1 output. Random forest, just to give you a brief introduction, and if you have detailed questions, certainly feel free to ask them in the Q&A section. But random forest is capable of dealing with many independent variables and nonlinear relationships, noisy data that are spatially influenced, and with a large quantity of data, all conditions that we have represented in this data set. Okay. Random forest is a type of classification and regression tree that is bootstrapped, and we leave a third of the data out, grow a tree where across those node splittings are statistical clouds across nodes, and saying what explains these splits and variation, what variables are important, and then predict to our withheld data. And what you're going to see as some of our outputs is how much influence or how important a given variable is in those models. The farther to the right the dot is, the more important it is. And we used a selected model framework where we used some methodology that we developed in previous work to actually be able to do model selection and say which of these variables are actually contributing to our overall model, and to scale them so that the most important variable is always a 1, so that you can have a frame of reference or models are comparable between each other. Okay. So we have our 3 RapidEye time points of a dry, moderate, and wet condition, estimate probability of it being a wetland, and come up with a cumulative sum probability across all of those RapidEye scenes, so across all 3 of those types of conditions, or 3 years. And those models worked extremely well. The out-of-bag error ranged from 3 to 15%. Most of it was in the single digits. The classifications were consistent in how well they performed across different areas and across dry and wet conditions. You can use that to identify that maximum wetland extent and then scale up to our Landsat data. So we identified that maximum wetland extent across from the summed probabilities, and then said, okay, we're going to use this to train our Landsat data to see if we can scale up to 30-meter data. So we took a 10% random subsample that was distributed across that probability gradient. So some of that sample came from those locations that had a very high probability of being a wetland, and those to having being a lower probability wetland, but constrained to the maximum extent of the wetland. So all wetland samples, and then training data that also represented non-wetlands. Okay. So now we have our wetlands, a prediction of probability of being a wetland from our 5-meter data, and want to scale up to our 30-meter Landsat data. So classification of our Landsat data, and we have 6 years that are represented, 2 that are wet, 2 that are dry, and 2 that are moderate conditions. And for each one of those years, 3 time points across the growing season. So beginning of the growing season, mid-growing season, and then a time point that's close to plant senescence. So we have 18 scenes for each of these areas to get an overall time series. And I want to give you an idea of what this time series looks like. So hopefully this animation is showing this is across 18 scenes from one of the sample areas in North Dakota, and it's giving you how much variation, a picture of how much variation we have across seasons and across years in what is a wetland and what areas are highly ephemeral and what areas are dry. So the wetlands are represented in blue. The redder it is, the drier it is. So across those 18 scenes, we calculated the proportion of times that a random point was classified as a wetland, and then used that based on natural statistical breaks to come up with designations of highly ephemeral, ephemeral, and permanent. Okay. So now we have that measure of ephemerality, and we want to link that ephemerality to climate. So we know that on wet years that our wetlands are bigger, that they last longer, but we want to formally link that ephemerality to climate stochasticity. So then we can make some predictions about what's likely to happen out here in the future. So just as a refresher, we have some of our permanent wetlands, we have ephemeral wetlands, and then we have our highly ephemeral wetlands. Give you an idea of what these wetlands might actually look like out there on the ground. Want to link that to climate data. So we have climate stations from across the PPP LCC and pull down monthly data and summarize these across the time series of Landsat data, so 20-some years. So again, another massive data set to be able to link that climate time series to our Landsat data. And from those climate station data, we calculated multiple statistics off of, or metrics, from precipitation and temperature, trying to get median, mean, and also extremes, and understand what about this climate is really driving the system in relation to wetland ephemerality. What's important for you to get from this table is that some of these variables are related to precipitation, some of them are related to temperature, and then we have a conditional sum of the precipitation that's snow. And that snow component is going to become really important here down the line. So again, we have these classes of permanent, ephemeral, and highly ephemeral wetlands. And we want to use our random forest approach to predict for a given pixel if it's going to be permanent, ephemeral, highly ephemeral, and relate that to climate. So that relationship with climate. And what you're looking at is this graph of overall importance of given variables. So the farther the bar is to 1, the more important that variable is, especially if you look at that top purple bar. Down the side, we have our different variables where snow is on top. This is, if you have a T, those are temperature variables. The PPT are precipitation. So we have different measures of the statistical distribution of temperature and precipitation. So minimum temperature over the year, coefficient of variation and precipitation, maximum temperature, the lower bound, the upper bound on maximum temperature, and precipitation year to date. Okay. These are all variables that out of that whole long list you saw, these were the ones that were retained, so they're significantly contributing to overall model performance. They're actually important in making our predictions. The colors of the bars, the purple is overall model, how important was that variable, and then we can also break this down to say for a particular class of wetland, if you're a permanent wetland, an ephemeral wetland, or a highly ephemeral wetland, does that change as far as where the predictive power was? And you'll see a little bit of variation in that for our permanent wetlands, predicting whether a wetland is going to be permanent is highly related to snow. It's important for everything, but it's really driving that. Snow is really driving that permanent classification. And that lower bound of temperature, so how hot it is on that lower bound, really has a lot of predictive power when it comes to predicting highly ephemeral wetlands. That makes a lot of sense. That snow is that moisture availability. The maximum temperature, minimum bound of that maximum temperature is giving us how hot it is. Okay. Remember that random forest is an ensemble of weak learners. We're creating a weak model, predicting to withheld data, and looking at model fit across all of those. So sometimes our internal fit statistics can be low, And then we want to look at a completely withheld data set to look at accuracy, find that our overall model accuracy is quite good. Our error is less than 20%, which, given how stochastic these data are and how much wetlands vary from year to year, and that we're only using climatic data to predict those differences and not things that people are doing out there to drain them or dig them out to provide more water for cattle, that we have a huge amount of predictive power, and that our class error is relatively even across our classes. So these highly ephemeral wetlands are very stochastic, but we're able to predict them just as well as our permanent or ephemeral class. When we look at what variables are important across all of these, how many times it was important across the overall model or our three classes, it's another way of looking at that same information. The snow really is important for everything, so is that lower bound on the heat, the maximum temperature. So this is building a model across all of our time series. We also want to say, within a year, what is it about the climate in that year that could predict how ephemeral a wetland is, say, in 2012? So we also did a within-year model. You'll notice that our final model has a lot more variables in it, so we have less information because we're looking at each year, and we also have more noise, right? So that's going to have a lot more stochasticity. So it's not surprising that we need more variables in order to explain what's going on. Important things to note, that snow parameter is still a driving process for our overall ephemerality of wetlands, and so are our maximum temperature variables. So we're still getting the same message even though we have more parameters in this overall model. If we look at that importance frequency, so again, how many times was that variable important across all of these different models for a given threshold? Snow, still really important. We have also those components of temperature and the extremes of temperature. And one thing that's really interesting to notice is that we expected that we have variation from year to year. And if climate wasn't really driving that, or if we didn't have enough power to explain that, you would expect to just have a huge year effect. And year is not actually important at this threshold across any of our categories. So they're really explaining this by climate and not just something else about a year-to-year effect, which is valuable to know. All right, so we've quantified wetland ephemerality, we've linked that to climate and variation in that climate, and then we want to say we want to predict that ephemerality for future climates. And remember that we have a lot of uncertainty in what that future climate might look like. So we could, depending on what GCM you're looking at or what emission standards, you could get 10% less precipitation to 20% more precipitation, no change in temperature to 15% increase. And then if we use these parameters to say, okay, let's go back to how we calculated snow and look at amount of precipitation that comes below freezing, we could have 40% loss in snow to 10% increase in snow. And we have this relationship that we've already built between ephemerality and climate, and we want to take that and tweak those climate parameters and say what is likely to happen to our classification of our wetlands based on future climate conditions. And there are 5 ways that we could expect that our wetlands might change. We could get a shift from more of our wetlands shifting from highly ephemeral to ephemeral and from ephemeral to permanent. And again, from both of these classes into the permanent class, so those would be more permanent wetlands on the landscape. We could have a similar scenario where things are shifting in the other direction, so we end up with more dry wetlands out there on the landscape. And we could also get changes where we expect our highly ephemeral wetlands to go to ephemeral and our permanent wetlands to go to ephemeral, so we have more ephemeral wetlands on the landscape from the shift toward the middle. Okay, so these are the potential futures that we could look at. So what we find is if we take that parameter space, that potential increase in temperature, our loss to increase in precipitation, and changes in snow, and we simulate all of those possible conditions and use those simulated conditions to go back through and re-predict our model, what we find is that depending on where we are, we could get shifts to more permanent wetlands, more ephemeral wetlands, or more dry wetlands. The important thing to note from this figure is even if you get increases in precipitation, the vast majority of our futures have more of our wetlands being more ephemeral or more dry in those future conditions, even with getting more precipitation, because the form of that precipitation has changed where we're getting less snow. We're seeing that across all of these potential futures, that we're getting more ephemeral wetlands out there in the landscape. And this has implications for water quality, where if we look at our water quality data in relation to the type of wetland, so is it highly ephemeral or ephemeral, we see that ephemerality is linked, there's a positive relationship between ephemerality and conductivity and alkalinity, so that there may be a degradation in water quality across the landscape as wetlands become more ephemeral. So, in summary, we are able to do highly accurate wetland classifications with extremely low classification error rates for both the rapid eye and scaling up to the Landsat data. Snow is critical for wetland persistence. So this slow recharge from snow melting gives us less ephemerality in our wetlands, regardless of what happens with precipitation later in the year. So we really do have a recharge that's being driven by snow. We expect to see an increase in ephemerality with wetlands with climate change, even if we get more precipitation. And we have developed this wetland mapping protocol that could be cost-effective and semi-automated and give a gradient, so the probability of being a wetland, and be able to do that across time. So look at how wetlands change across time as we potentially get into different future climates. All right, so what we would like to do going forward with this project, dependent on funding, would be then to look at quantifying wetland ephemerality and moving this forward into using new data and scaling up even further from our rapid eye data and saying how far can we push this? How can we use this subsampling relationship? And then use those, make spatial predictions of wetland change and assess the consequences for ecosystem services. So quantifying the wetland ephemerality, so this is building on our previous work. One thing that's new and really exciting and fantastic is we have Landsat 8 data that were collected as of last year throughout the same period where we were out in the field. And just based on some preliminary information, we'll be able to show that based on Landsat 5 data, we had very low error rates, but they're cut almost in half using the Landsat 8 imagery, has a slightly higher dynamic range, and there also is the blue edge band, which is very powerful for detecting wetlands. So we want to be able to, we have this rapid eye subsampling that we were looking at stacking Landsat on top of the rapid eye, but we'd really like to know, can you use rapid eye as a subsample and go to scenes outside of the rapid eye and say we have our rapid eye image, and can we look at the 8 nearest scenes around that rapid eye image in addition to the one that overlaps, and be able to use that subsampling approach across a larger footprint on that landscape. This ends up with a pretty big sample area for each one of these, and what we'd like to do is to have 2 of these areas for each ecoregion, which ends up being over 7.5 million square kilometers of predictions of wetland ephemerality and what that wetland ephemerality might look like in the future. Okay, so then we'd like to make spatial predictions of wetland change. So we've predicted what that wetland change might look like across these different scenarios, but use our same overall model framework, and then say we have these relationships of what this might look like in the across future conditions, figure out how to collapse those together and predict the future ephemerality and the uncertainty in that future ephemerality for our future climates across the PPP LCC. And then really what the golden chalice for a lot of these projects is to then link these things to consequences for ecosystem services. So those things that we really care about in addition to ephemerality of wetland and what they mean for the system. So we already have this potential link between quality and water quality and wetland ephemerality. So we would like to go and do validations on the spatial predictions, collect additional water quality information for a suite of type of wetlands, and relate water quality to wetland ephemerality. And our ecosystem services of assessing effects of water filtration and water production across ephemerality classes. It also has implications for waterfowl production, critically important for the PPP LCC. In addition to wetlands being important in themselves, wetlands are a measure of wetness in the landscape. And because of this, as we have shifts in the probability of areas being wetlands or ephemerality across the landscape, wetlands can be used as an index of overall productivity. So we would like to use NDVI or SAVI or measures of plant productivity, link them to wetland ephemerality, and be able to make predictions of potential consequences to plant productivity in the PPP LCC by using wetlands as an index of that productivity. And the implications for plant production and livestock production in the PPP LCC, as well as crop production more broadly than just in a given wetland. Okay. And so just real briefly, I'm going to turn this over to Charlotta Gabrielson, who is a PhD student here at University of Wyoming, and her PhD dissertation work sits on top of this project, and I just want to give you a little idea of other ways that these data can be used. All right, so as Melanie mentioned, this work to quantify wetland ephemerality does lend itself to a number of additional research questions. So it has many broad applications to ecological questions, some of which I'll explain here. So first, I'm looking to address the effects of wetland ephemerality on wetland biodiversity, and specifically measured by amphibian, microbial, and plant community diversity. And we know that these various taxa are dependent on wetlands, but also that they contribute to overall wetland function. So to quantify specifically amphibian and microbial diversity, we'll use environmental DNA analysis. And this is essentially a way to molecularly detect selected species of interest from filtered water samples from the field. And this were taken during wetland surveys and have been collected as a side part throughout this project as well. And we essentially extract DNA from these filters and then use quantitative PCR to assess which species are present in those wetlands. And there's been a number of studies that have shown efficiency and effectivity of doing this. So another potential research aspect here is to look at amphibian connectivity. So looking especially at how we quantify the effects of ephemerality on amphibians, and looking at how potentially ephemerality can influence structural connectivity across the landscape, and in turn how these amphibians use wetlands across the landscape. So to do this, we'll be using a landscape genetics approach in which you correlate environmental factors in the landscape to genetic diversity measures. We'll be looking at 3 different species that occur across this part of the region. So this, just going back for a second, is the environmental DNA analysis to look at biodiversity. So this is an example of 3 different species here, and the results from quantitative PCR. And as you can see in these curves, essentially where you get the higher peaks is where we detect these different species. So in this case, we're looking at 3 separate amphibian species in this case. And so again, this to ecosystem services and really strengthening the connection to biodiversity production of these wetlands, and especially in linking this to wetland ephemerality as well. So then, looking at amphibian connectivity across the landscape, and just to emphasize the importance of ephemerality in this connection, when you look at a landscape, you essentially have a set of local populations that interact via dispersal. And this is really important in terms of looking at the landscape matrix. So we have these metapopulations, however, under given situations, so where we might have higher ephemerality, these local populations might go extinct. However, typically these metapopulations can persist by
recolonizing these different populations, so essentially rescuing these populations. However, climate change, and especially in the prairie pothole region, threatens these connections, and with increased ephemerality, we might have lower functional persistence for particular species that depend on these wetlands for breeding and also connectivity. And lastly, this really just strengthens, again, as an ecosystem function for wetlands, to really promote connectivity across the landscape. So estimates of ephemerality are hopefully able to provide a greater understanding of how these wetlands facilitate connections across the landscape overall for both wetland-dependent and independent species. All right, and with that, we have many people to thank, and I'll turn this back over to Melanie for any questions.
All right, so there are a huge list of people on this slide that without whom this project would not have happened, including the PPP LCC. And there is a list here in the middle that are people that helped with and made possible access and logistics, which across this huge region and the amount of private land that is in the PPP LCC is not a minimal task. It requires huge assistance from a wide variety of folks, and we really appreciate their help. And also with field technicians that have been involved on this project who, without their persistence in being able to trudge through wetlands and take GPS locations in the pouring rain or heat, this would not happen either. So really appreciate their help. And with that, I think we have time for some questions.
Well, first of all, Melanie and Jeff and Joanna, thank you very much for the presentation. The work is terrific. It looks like it's got some applicability, as you said, to a number of different issues. I guess my first question might be relative to the snowfall being the big driver, and I wonder if you considered maybe associated issues with the depth of frost, sublimation rates in the winter, and how that might also affect what the snowfall seems to be driving in these wetlands, and how those changes might change the hydrology of the systems as well.
Yeah, so that is a really extremely good question, and one part of that, so the frost-free period and also the extremes in coldness are in these same models as covariates. And so there can be interactions there, but really that overall driving snow is the major signal, and not those like how cold was winter, how long was the frost. Having said that, we don't have, there's a lot to be learned about hydrology of wetlands and how much of that recharge is coming from surface water versus subsurface versus deep surface recharge of wetlands, and how that is happening. And because we have such a strong signal with snow, one of the things we really think is going on is that we're getting the slow release of moisture, and whether that's coming from surface or probably more likely subsurface recharge and soil moisture. But there certainly could be an interaction in how that, how frozen that soil is at a given time compared to melt. And if you got a rain on snow events or cases where snow is melting off quickly but the ground is still frozen, that could really change that dynamic. And so that is a really important consideration. I don't know, Jeff, if you have anything to add to that.
Yeah, I add that, so I mean, one of the that we're doing in this study, a nice addition, is that we are considering timing, and lots of climate modeling efforts don't think about timing. They're just looking at the pure interaction between temperature and precip. In this particular model, we utilized PRISM data, which was measured on a monthly time step. And we're working right now on digesting actual weather station data and getting down to hourlies. So the resolution, the temporal resolution of what we'll be able to feed into these models will be considerably greater. And working on methods for deriving spline-based climate surfaces for the spatial predictions. So we're still bringing together some pieces to give us more detailed information to potentially get at questions of what you're talking about. It's just we kind of need the resolution to get there.
Other questions?
Yeah, I'll throw one out. This is Jeff. Regarding the hydrology thing and the stratification uses ecoregions, and one of the components, if I recall, of ecoregions is the soils, which might get to the subsurface-surface relationship of hydrology. You guys consider that in your stratification, or looked at soils maps on a landscape scale as a way to interpret these data?
So the idea with the stratification was just to make sure that we're capturing the variability that's out there across the PPP LCC. And so those components aren't directly then used in the analysis. We're making sure that we have the ecoregions represented and the drying risk, drought risk that's represented from across the whole region. We didn't include soil types in this model, and the reason for that is that we really wanted, our questions are really driven about linking ephemerality to the climatic forces. Having said that, there could be cases where the soil is interacting with the climate, which is something that we might want to consider. Using soil data because it's categorical and because of the scale that it's mapped on, there are some complications from the modeling side of being able to use those data. We know the soil is really critically important. This issue comes up again and again and again in these kind of modeling efforts of how to incorporate soils data because of the type of data that we have for soils, and it's a little bit difficult to use.
I mean, there's other characteristics in soils that start affecting hydrologic recharge as well. So, like every time you strip away one piece of the puzzle, you're faced with the next one of some really bizarre structural rock characteristics that affect recharge out on the prairie pothole region, as opposed to, say, eastern Montana. One thing I will say is that we did put a block effect in our model,
yes.
And that block effect is accounting for the variation based on our stratification. And so we did notice some partitioning of variance based on that block effect in our model. And I think we need to, so it's controlled for in the model, but now we want to understand it. And we realize that there are regional climatic differences across the ecoregions, but there are also a lot of soil and geologic characteristics that vary.
And having said that, though, in the overall model, the block effect was not retained, I believe. It was retained in the yearly model. Yeah, the block effect was. But yeah, and so that's a way to account for these regional differences as we have, especially we'd like to add more replicates of the rapid eye data, but that you have that regional differences, which is partly soil that is accounted for. But it didn't have an overwhelming effect on the model, which is interesting in of itself. How much of that is really being driven by climate?
Right. Thank you.
Hey, do you know Chip Eulis at Northern Prairie?
No.
I'll hook you up because Chip and a whole bunch of folks a number of years ago published a paper called the Wetland Continuum Concept.
Oh, yeah.
And it deals with
charge,
that whole thing.
Yep.
And Chip and a whole bunch of other people are about to come out with kind of what I'll call version 2.0 of that paper. And there's a lot of it dealing with salinity and shifts in salinity in these complexes. And the other person that you might want to touch base with regarding the issues of hydrology is Jim LeBaugh, who's out in Reston. Stoner, I'm surprised you didn't mention him. Who did a lot of work with Chip and years ago out at the Cottonwood Lake Study Area, looking at quantifying the whole recharge flow through discharge question and water chemistry related to all those things as well. So the point here is that the paper that Chip et al. Did on the continuum could seriously, this information could seriously modify that as we move forward with some climate shifts.
And we are very familiar with that paper. has some light bulbs coming on across the room. And I think one thing that's really important, and I didn't explicitly state this at the beginning of the talk, is that there are all sorts of things that could contribute to wetland ephemerality. And some of those could be underlying geology, some of them could be anthropogenic effects. And what we wanted to understand was the piece of that was related to climate so that we could look at changes in future. So we're really looking at wetland ephemerality in relation to climate and how much of that is explained by climate, with the realization that there are all sorts of things going on in systems, but how might ephemerality change given changes in climate under future scenarios?
Hey, Neil, are you still on?
This is Melanie.
I was wondering if Neil Nemeth is still.
Oh, sorry, I thought you were talking to me.
Apparently he's left.
Or he tried to unmute his phone and
hung up, yeah. Well, Neil and others have been doing a lot of work on this kind of a question as well, and I was just going to kind of try to pick his brain a little bit, see if he had any specifics he might want to add based on the research he's been doing. But he's apparently not on the phone anymore.
How about some folks over at ARS? John, you got any questions?
No, it was really interesting because I know that Rebecca Phillips, who was here before, had done some looking at wetland hydrology also. So yeah, I enjoyed the presentation.
Thank you.
So we're still kind of keeping a dialogue open, actually, with Neil and more via Kevin Doherty, on how in the longer term to start relating some of these effects to changes in expectations of duck settling patterns, and so actually tying it into some of the regional fish and wildlife priorities. And Kevin and I have a paper in review right now that's done some non-parametric modeling in understanding these settling patterns based on the Transect data, and we're pretty keen to feed that back into some of these models to understand in future novel climates if we're going to see some unsettling effect.
Neil just joined us in Mike's office. He was having problems with his phone, so I'll ask Neil the question again. Neil, you've been working on wetland stuff for a long time and climatic types of issues. You want to get anything to add or question specifically regarding the presentation? Or gaps that you see that we need to address based upon things you've been working on too?
The biggest thing that I would point out has been a lot of work that's followed up from Johnson has done, talk about drying out, but we're not seeing drying.
Neil, you're really breaking up.
Okay. No, I'm just saying that we're not seeing a lot of the patterns that had been predicted about drying out in the prairie pothole region, at least not in the last 40 years. There's actually been an increase in the number of May ponds. Might relate back to some of the timing issues you were talking about. But when we've also looked at, they've discontinued the July production survey, but first they had a July production survey. We weren't July ponds either. So that's one of the big questions is what's really happening, because the data we have suggests that the climate predictions that were made aren't driving.
We're only getting about a part of every third word. Sorry.
I guess I just have this effect on phones. The climate predictions that Carter Johnson and his crew made relative to wetlands are not being expressed in the wetlands that we're seeing out here with these as far as the waterfowl survey data goes. So that's one of the big questions is what's actually happening with long-term wetlands conditions.
Yeah, so I think got at least part of it. So the question was about the Carter Johnson predictions and not seeing some of those play out on the ground and kind of wondering what's going to happen long term with waterfowl. Was that the question?
Well, with the wetlands.
Oh, with the wetlands. Yeah, and I think you know, part of the complexity in all of these scenarios is that there are just so many possibilities of what the future could look like, that it's that uncertainty and that stochasticity makes making a single prediction difficult. And so I think one of the strengths that we're trying to build on in this particular example is that simulating across those potential futures and saying, if you get no change in temperature and increase in precipitation, what are the expectations for change out there in the landscape, compared to no change in precipitation but an increase in temperature, what are those expected changes? And so across that whole potential future simulation that we did, there are a set of conditions where you might see more permanence in wetlands based on those conditions, but the vast majority, 80-some% of those simulated potential futures, the prediction is for more ephemerality in those wetlands. And so it really depends on what happens, which potential future we end up in, as far as we get shifts to more permanent or less permanent wetlands, or wetlands drying out more quickly. But the majority of those cases are for shift to more ephemerality in a wetland. Jeff, if you have a follow-up.
I mean, the nice, fun 3D manifold that we showed. So the way we're doing this is Monte Carlo simulations, and we're setting the bounds of the Monte Carlos based on the extremes of the GCMs. So we're trying to simulate through an entire statistical space and see what the influence. There's a convergence function that goes on, and see what the more likely outcomes are going to be, and what, given all these possible combinations of what these disparate GCMs are telling us, what are potential outcomes that we're going to see. And we're actually seeing some consistent patterns, and this is how we're teasing apart this relationship. Regardless of increase in precip, that you get a temperature offset of that, and that's where the timing factor comes in. So you get these three things interplaying in that statistical space that actually is giving us a pretty informative answer, even though there's so much disagreement with what the climate science is telling us. So hopefully we'll be able to relate that agreement to on-the-ground management decisions as we go forward with being able to do spatial predictions of this.
And kind of the idea we have is to be able to have something akin to like a transition likelihood for a given wetland that's taking into account that Monte Carlo simulation. So that variation, or that uncertainty, and what could happen, and what is likely to be the most likely trend for a given space, but also the uncertainty around it as we move forward into being able to make some spatial predictions.
It looks like we're rapidly approaching the top of the hour. Thanks again, Melanie and Jeff, for a very informative webinar. Ashley, I don't know if you're still with us, but we'll be sending out some notes to the entire tech team here in the next couple of days, including some description of how we're going to go through the review process. And for those who are not signed up on the website, how to get your access to the back door of the website, where we'll be posting the 28 proposals for review, along with criteria and the spreadsheet for ranking and reviewing. Ashley,
yeah. Hey, Mike, it's Ashley. I'm here, and I'm happy to, if folks have any questions. We did send out kind of a guide quite some time ago on how to access the online workspace, but we can resend that information out to folks just in a little bit more detail. It's very simple if you haven't registered yet, but that's where we'll be housing all of the proposals. So as you have questions, don't hesitate to give me a ring, and I can walk you through it.
And Rick, you were out of the room when we talked about the steering committee meeting, but ultimately we're going to have this review and ranking done by the end of the month. We're going to have a discussion about that next month at this time, provided to the steering committee within a day or two after that, and they are scheduled sometime the week of the 7th. Yes. Okay.